The interstellar object 3I/Atlas, discovered in 2017, has been a fascinating subject of study for astronomers. It is not just its origins and interstellar journey that intrigue scientists, but also its behavior as it approached the Sun. One of the most interesting aspects of its study is its rotation and how it might have changed during its perihelion, when it came closest to the Sun on October 29, 2025. When studying the rotation of 3I/Atlas, astronomers use two primary methods. The first involves observing the periodic shift in the orientation of the jet structure launched by the object as it rotates. This method allows astronomers to trace the behavior of the object's rotating body based on the changes in the jet's direction. The second method relies on analyzing the periodic modulation of the total brightness of 3I/Atlas, including the glowing halo of the coma and the jets around it. These two methods provide complementary insights into the object's rotation and how it changes over time, particularly in response to the Sun's gravitational and radiative influences. A study co-authored by Tony Scarmato and myself in 2025 took a closer look at these two methods for measuring the rotation of 3I/Atlas after perihelion. The results of this study offer new and intriguing insights into the nature of the object's rotation during its closest approach to the Sun. We conducted the first set of observations by measuring the position angle of the anti-sunward jet in Hubble Space Telescope images. These images, captured between November 20th and December 27th, 2025, were analyzed using a specialized method called the Larson-Secunina rotational gradient filter. By tracking the changes in the position of the jet, we were able to derive the rotation period of the object. The second method involved using data from the 0.25-meter telescope MPC L92 in Calabria, Italy. Between December 9th and December 22nd, 2025, we measured the periodic brightness variations of the object, which also provided a value for the rotation period. The results from both methods were remarkably consistent. The first method, based on the position angle of the anti-sunward jet, yielded a rotation period of 7.20 plus or minus 0.05 hours. The second method, based on the brightness modulation, returned a slightly shorter period of 7.136 plus or minus 0.001 hours. While there was a small difference between the two values, this difference is likely due to systematics and aliasing, which are common in such measurements. Nevertheless, both sets of data suggest a post-perihelion rotation period of around 7.1 hours, a strikingly short period compared to the earlier measurements taken before perihelion. The precession of the jet structure around the rotation axis of 3I/Atlas, which was observed after perihelion, is one of the key pieces of evidence for this conclusion. The periodic shift in the jet's position suggests that the object is rotating with a period of about 7.1 hours, which triggers the precession of the jet structure. This phenomenon is fascinating because it implies that the rotation axis of 3I/Atlas is almost perfectly aligned with the Sun 3I/Atlas axis, with an alignment of within 20 degrees. This alignment is unexpected because the rotation axis of 3I/Atlas was set far away from the Sun in interstellar space. The exact cause of this alignment remains unclear and warrants further investigation. One of the most striking observations from our study was the way the mass loss rate of 3I/Atlas changed as it neared perihelion. In the months leading up to its closest approach to the Sun, the mass loss rate from the object increased significantly. This change had a major impact on the modulation of the brightness observed around the object. The increase in mass loss meant that the periodic variations in brightness observed after perihelion could no longer be attributed to reflected sunlight from the surface of the nucleus alone. Instead, the variations were largely driven by the glow surrounding the nucleus, including the coma and jets. This finding is crucial because it shifts the understanding of the periodic brightness variations. Rather than being caused by changes in the reflective properties of the rotating nucleus, the variations in brightness were primarily due to changes in the distribution of dust and gas in the coma. As the object rotates, The outflow of gas and dust from the active areas on its surface sweeps around the rotation axis, resulting in periodic variations in the observed flux. These variations occur because the jet alternately points closer to or farther from the line of sight, which affects the column density of dust along the line of sight, the distribution of dust within the photometric aperture, and the scattering phase function of the dust particles. In simpler terms, the periodic variations in brightness can be understood as a form of heartbeat variability, where the jets pump dust and gas into the coma, like blood being pumped through veins. This mechanism is similar to the way the periodic modulation of the jet's position angle causes changes in the observed brightness. The direction of the jet is tied to a fixed active area on the rotating nucleus. So as the nucleus rotates, the jet undergoes precession, producing the periodic shifts in the position angle. These shifts are then reflected in the observed brightness variations as the jet alternately points in different directions. This new understanding of the object's behavior also sheds light on the differences between the rotation period before and after perihelion. Before perihelion, the rotation period inferred from the brightness variations was significantly longer, at around 16 to 17 hours. This is more than twice the rotation period measured after perihelion. The difference between these two values is likely due to a combination of factors, including changes in the number of active jets or active spots on the object. These changes may have been triggered by the perihelion passage, which could have altered the illumination geometry and caused additional active spots or jets to form. One key aspect of this shift in behavior is the alignment of the rotation axis of 3I/Atlas with the Sun 3I/Atlas axis. Before perihelion, only one of the rotation poles was illuminated by the Sun, but after perihelion, the second rotation pole was also illuminated. This change in illumination could have triggered the formation of two active jets, which would have been viewed from a different angle after perihelion. This shift in the number and orientation of the active jets would have contributed to the observed differences in the brightness variations, as well as the precession of the jet structure. The discovery of a rotation period of 3I/Atlas after perihelion is a significant step forward in understanding the behavior of this enigmatic interstellar object. It also highlights the importance of combining multiple methods of observation to gain a fuller picture of an object's rotational state. The agreement between the two independent measurements of the rotation period supports the conclusion that 3I/Atlas has a post-perihelion rotation period of around 7.1 hours. Further studies will be necessary to explore the reasons behind the alignment of the rotation axis and to understand the physical processes that govern the behavior of 3I/Atlas. The perihelion passage of this object appears to have had a profound effect on its rotation and activity, triggering a series of changes that were captured in both the brightness variations and the periodic shifts in the jet's position angle. These findings offer new insights into the dynamics of interstellar objects and their response to the gravitational and radiative forces of the Sun. As we continue to monitor 3I/Atlas and other interstellar objects, we can expect to learn more about the factors that govern their behavior and the processes that drive their activity as they travel through our solar system.